A couple months ago, I put out a video on common misconceptions about the delayed choice quantum eraser experiment. Since then, the video has been getting some comments. One of the themes in the comments is people saying, I don't know what I'm talking about, that I don't understand the experiment. Or, a little more charitably, that the video doesn't really explain the details of the quantum experiment. It completely glosses over them. And that's actually true. When I made the video, I intentionally didn't talk about the details of the actual experiments that people have run. It's not because I don't know the details, it's because I think the details are a distraction from the core issue. But okay, looking at the comments, I can see that if I don't want to get chewed out, then maybe I should cover the details. So that's what this video is. Strap in, because we're going to get technical, and we're going to reproduce the first ever delayed choice experiment. There are two things we need. First, we're going to need the layout of the original experiment, and we can get that from the paper. So we go to Google Scholar, and we search delayed choice quantum eraser. And the top result is the right one. And Google Scholar almost always gives an open access link to the paper. So here's the paper, and we can look through it for a figure showing what we want to make. And that's it right here, figure 2, a schematic of the experimental setup. The next piece we need is a way to actually build this. And I don't mean build it in the real world, I just mean build it in a simulator, in a virtual lab. And the virtual lab we're going to use is called Quantum Flytrap. And they have this sort of nice editor where you can place down optics components and see what quantum mechanics says they'll do. So let's get the lab and the paper on the screen at the same time. Like so. So let's start translating the pieces. So first we need our entangled source of photons. In the virtual lab, we get that with a BBO crystal. One minor difference between the experimental setup here and what's happening here is that in the experiment, they're creating photons whose paths are in superposition, whereas here we're creating photons whose polarizations are in superposition. Or, whose polarizations are entangled, and here the paths are entangled. We can turn the entangled polarizations into paths using a polarizing beam splitter. So there's two possible polarizations. The beam splitter splits them in two, and we can check which one hits something. So this is our equivalent of the signal photon path. It's not exactly the same, but it's basically the same. We'll be able to see the same data coming out of the system. So next, let's make this part here, which is the eraser. And I find that it's easiest to make this if you start from this kind of central element, which is this beam splitter. So let's put that over here somewhere. And there are mirrors bouncing things into the beam splitter. Like this. And on the opposite sides of those mirrors, there are detectors. So there'll be one here, and there'll be one there. And then we have to bounce light into the system. Again, because these are polarized, because these are entangled polarizations instead of entangled paths, we have to use the polarizing beam splitter to split it into two cases. Like that, and we can bounce it in. There's one last little difference between how this behaves and how this behaves, which is that the way this is currently set up, the eraser is going to have the opposite effect of what we intend. Like instead of the eraser case being the wavy case, it's going to be the flat case. And we can fix that. I'm not going to go into why this works. I'm just going to do it. So with this little tweak, it'll make things the right way around. Right. So what do we have left? We have the choice part, which is these beam splitters along these arms that bounce out of the system, one of them into a detector. So there'll be a beam splitter here bouncing out, a beam splitter here bouncing into a detector. And now we basically have everything except the coincidence circuit. Now there's not really a coincidence circuit in this virtual lab, but there is a way to do it, or at least the way that I found that I can do it is I can use a bomb. And the thing about bombs is that you can control whether or not they absorb photons or not. So this detonates if a photon hits it, but I can set this absorption to 0 so the photon goes straight through it instead. And additionally, if you hook a bomb up to a wire, whether or not the wire is powered or not can control the absorption of the bomb. So what I found I can do is I can make an AND gate and power the bomb from the AND gate. And then I can have two inputs into that AND gate. And the bomb will only be opaque if both inputs are on, if I set it up that way. And now if I add a laser here, we can see when both inputs are on, we hit the bomb, but if one of the inputs is off, it goes through. So instead of these variables, we can instead run it off of detectors. So I can hook the AND gate up to this detector, and I can hook this other input up to this detector. And now the bomb is telling us how often they fire together, except that you actually need to make sure that this photon coming out here arrives later than this would be hit. So currently it's way too close. And if we step forward through the simulation, we can see that like the reader photon has left the system and this one over here is still moving around. So we need a lot more delay. Let's actually move this out of the way and bounce this all around the sides. And then we'll need an AND gate for the other one as well. So we power it from this detector and from this detector. Or, yeah. And we make a second bomb, which is also set up to be transparent when unpowered. And I'm actually going to shift this whole thing down to make sure that the reader photon doesn't get into the works. Okay, good. Now I'm going to be moving these two wires around a lot, so I'm actually going to connect them to an intermediate. So they only have to move one wire in order to condition on different detectors. Anyways, we now have all the pieces of the experiment. We have our source of entangled photons, the BBO crystal. We have our signal photon path, which is this one here. D0 is these two things. Basically, like these represent two possible places that you could hit on the screen. And then we have our choice mechanism in these two beam splitters. One of them goes to D3. So this one is D3. And then we go into the eraser mechanism, which has detectors D2 and D1. And D2 is the one that's closer to D0. So that's this one here. This is D2. That which would make this one D1. Okay, so we have everything set up. And now we just have to check if it works. We have to see if we can reproduce the data from the paper. So here's the data that we want to reproduce. Now, obviously, we're not going to be making these very fine-grained plots. Like our screen is only 2 positions instead of they use like 30 here. So instead, we're just going to be looking at, is it flat or is it not flat? So this, what we're looking at right here, to be an example of not flat. So one of the bombs never goes off, and the other one does when we condition on D2. So it's low, then high. So we're interpreting this as a wavy distribution, or as the massive simplification of a wavy distribution. And that is what we're supposed to see. So if we look at figure 4, zoom out a little bit. Joint detection rate between detectors D0 and D2. This is a wavy distribution. And here we have a wavy distribution when we condition on D2. If we instead condition on D1, that's this figure here, we should also see a wavy distribution, but it should be the complementary distribution. So if you look very closely here, you'll see that the mountain in this figure exactly lines up with a valley in this figure. Wherever this one is low, this one is high. So when we switch from D2 to D1, we should see, instead of low, high, high, low. Let's check. Yeah, high, low. And then lastly, if we condition on D3, we should see a flat or a smooth distribution. So instead of seeing two different things, we should see the same thing. Okay, let's do that. And there you have it. So here we have a delayed choice eraser implemented in this virtual quantum lab. We have 3 detectors on the choice side. We have our screen, and they have the correct relationships between them, where this one gives flat and the other 2 give wavy. So one of the huge advantages of setting up the system in a simulator is we can then use the tools in the simulator in order to understand what is happening. In particular, we can look at the states of the photons over time by stepping through. Now, in order to really clearly show this, I need to increase the delay until this photon gets here. So I'm just going to rearrange things a little bit. Just put a little bit more delay. So that we can see if I step far enough that the signal photon has hit D0. The state of the idler photon is in a definite polarization. So if I back up to here, you can kind of see that the idler photon is stretching and squishing. This is how the simulator indicates that the state is entangled, that the polarization of this photon is entangled with something else in the system, in this case, the polarization of the other photon. But when the signal photon hits the detector, its polarization collapses as part of that process. And because of the entanglement between these 2 photons, the polarization of this photon also collapses. And so if we advance through time, we see that at this point, it's no longer stretching and squishing. There are different cases. So here we hit the right-hand side, but we could also have hit the left-hand side. Just go forward and back until I get the other case. Yeah, and so here we see the other polarization, the vertical polarization. And the key thing to understand about this system is that if you have a vertically polarized photon coming in to this eraser thing, it can only hit one of D1 or D2. So when the 2 possible paths that we've sent this photon down come together and meet at this beam splitter, they interfere with each other so that there's constructive interference along this path and destructive interference along that path, so that vertically polarized inputs always hit D1. So D1 is the vertical hit. Whereas if we'd had horizontal polarization instead at the start, which I can try to get to, there we go. Now it'll never hit D1, it'll only hit D2. So if we advance and we don't happen to hit into D3 or out of the system here, we got lucky again. Now we're heading towards D2. So D2 is horizontal. And the position that D0 hits here is also a measurement of horizontal versus vertical. This position here is horizontal, and this position here is vertical. So D1 versus D2 is actually a measurement of the same thing as left versus right on D0. So if we look at the laser view and we condition on D2, D2 means horizontal, and hitting the right-hand side also means horizontal. And so we always see that the bomb up here should get hit horizontal, except that I have messed something up. The delay that I put in here to make it a little bit clearer which state we're in actually made it so that we hit this after this photon gets past the bomb. I just have to get rid of this delay again. My mistake. Right, so if we hit the horizontal indicating detector, then we hit the horizontal indicating position. And if we hit the vertical indicating detector, then we hit the vertical indicating position. And if we hit this other detector, which isn't measuring horizontal versus vertical, then we don't get anything. So when I say that people explain the experiment backwards, that this is what I'm referring to. Instead of talking about how hitting D1 and D2 go back in time and determine which part of D0 you hit, you can instead think in terms of the part of D0 that you hit collapses the either photon into a particular state, which guarantees that it'll not hit D1 or not hit D2 accordingly. And that is an equivalent explanation for why you would see these patterns. And the benefit of this explanation is that it doesn't involve any time travel. You know, if you don't have to involve time travel in your explanations, why would you? Another thing that I want to point out about this is that it's sort of unnecessarily complicated. You know, a lot of the details in this setup are not really about making the experiment as simple as possible. They're just about making it possible to do it with the available technology. You know, in a simulator, we're able to much more freely move things around and have things just work. So, for example, in this experiment, they use beam splitters as the choice mechanism. But these are not really ideal choice mechanisms because we don't have control over them. It'd be much nicer if we could have a switch that we could flip in order to pick between the two choices. And in fact, we can do that. We can remove these two beam splitters. And instead of bouncing off these mirrors, just go through this beam splitter like that. Put the detectors afterwards instead of beforehand. And then have a switch that determines whether or not this beam splitter is present. So if it's powered, then we want the beam splitter to be present. And if it's not powered, we don't. So if we're not erasing, that's what variable 0 here means, then we get no wavy pattern. And if we choose to erase, oh, I've accidentally not conditioned on anything. So if we're not powered, get a flat distribution. So we're not erasing, flat. And if we just choose to start erasing, then we get a wavy distribution. We get not flat. And we can actually simplify this a lot more than this even. So I know that this is equivalent to powering this sugar solution, determining whether or not it's 45 degrees or 0 degrees, and then just get rid of everything except for these two things. And again, not powered, sugar solution 45 degrees, you get this flat distribution. If you choose to erase, then you get a wavy distribution. But now the layout is much simpler than it was before. And kind of the point I just wanted to make by doing this is the way that people normally explain and even think about the experiment is often unnecessarily complicated. If you just take the setup and you iteratively simplify it and simplify it and simplify it, you end up with things that are much easier to understand. And with this particular experiment, you can keep simplifying until you actually end up with something classical, which is what the other video is about. Anyways, I hope people found this a little bit interesting to take a delay choice eraser and actually do it in a simulator and see that it really works, but that, you know, the way people explain it is maybe a little bit misleading. I hope you enjoyed it.